Dear friends, welcome back. In our previous lecture, we demonstrated how to make a flat plate stable. So, before that we have derived an equation or the conditions for static stability for a wing alone configuration, and then we have taken a flat plate and then we mounted a weight to bring its CG ahead of the aerodynamic center, and we had a flight for it, right. Now, let us solve some more example problems related to this flat plate stability, how to enable the flat plate statically with static stability, right. So, we'll solve few example problems. Just before that, let us have a revisit of what we have derived. So, assuming this is my fuselage reference line, and say my wing error or chord line coincides with the fuselage reference line, and say this is my location of aerodynamic center AC of the wing measured with respect to leading edge of the wing parallel to the fuselage reference line. So, we call this as XAC of wing, XAC of wing, right. And say the CG of the system is located at a distance XCG, again measured parallel to the fuselage reference line, located at XCG of this entire aircraft. So, when there is flow, V infinity, so there is lift as we discussed earlier, and now we will not consider drag anymore, we will not account that, and we will also assume a small angle of attack so that the lift is entirely contributing towards this pitching moment about the center of gravity here. So, this is my CG, and we have moment about aerodynamic center, of wing. So, what we have derived is Cm naught of this aircraft has to be Cm AC of the wing plus CL naught of the wing times x bar CG minus x bar AC of wing, and at the same time we also looked at the Cm alpha. The sufficient condition is CL alpha of the wing times x bar CG minus x bar AC of wing. Okay. So, if this Cm alpha has to be negative, the CG should lie ahead of the aerodynamic center here, and so if it lies ahead of the aerodynamic center, so this term becomes negative. So, you need to choose a Cm AC of the wing, right, if you are dealing with a wing alone configuration in such a way that this value should be high enough to overcome this particular negative value, right. So, the difference between these two terms we'll talk about it in the coming lectures, what exactly this term, this difference talks about. So, in order to overcome this difference and the negative contribution towards the Cm naught, right, because of the CG lying ahead of the aerodynamic center, you need to choose an aerofoil with a strong CMAC or positive CMAC here. Okay. And then, yeah. So, let us now take up a problem. So, the question 1 for this week is consider a wing alone UAV with a wingspan of 3 meters, root chord of 0.3 meters and tip chord of 0.2 meters, tapered about C by 2 at any equation, C of y by 2. So, it is a midpoint, no? Tapered about C of y. If you consider any chordwise location, right. So, the taper axis lies at the midpoint of the chord. Okay. And weighs about 0.45 kg. The Oswald's efficiency of the wing factor E is 0.95. And say this wing is supported with a boom, the straight boom, near the straight boom exactly at the midway of span of length, .5 meters, and weight 0.15 kg. So the wing is also equipped or embedded with a 3-cell 3S LiPo battery, which weighs about 0.3 kg, and the CG the battery is at 0.15 meters from the or with respect to the leading edge of root cord. Okay. Question number 1 should be the first question you need to answer here. So let us say A. So what should be the weight of the battery? And consider, so here consider the CG of the wing coincides with the CG of boom. Okay, this is the question. And this is the data given, and the first question you need to answer is, what should be the weight of the battery, the weight of the brushless motor or say minimum weight of the brushless motor that need to be attached at the starting of the boom to enable this configuration Cm alpha less than 0. Okay. So this is what it is. So let's answer the first question here. So from the given data, solution. So what we are asked to do, we have a wing of 3 meter span with a root chord of 0.3 meters and a tip chord of 0.15 meter, and this taper happened to be the mid chord axis at each and every cross section. If you consider, like at a given chordwise location, the midpoint of that particular chord gives you the taper axis. And with a root chord of 0.3 and the tip chord of 0.2 meters, and this wing weighs about, say, 0.45 kg. That's what it is given here. So 0.45 kg here. So, and then this wing is supported by means of a boom like fuselage for it, right? So this boom length is about 1.5 meters with which weighs about 150 grams, right? So this is, and moreover, say for example, this wing is also, let us say, so we have a wing here and it is equipped with a boom, right? And then this wing is also equipped with a battery. Let us say this is a battery, and it is equipped with it is embedded with a battery, means the battery is inside this wing altogether. And say the wing, the weight of the battery is about 300 grams, and the CG of the battery is, say, 15 centimeters from the leading edge of the root chord. So this is my leading edge of the root chord. Say 15 centimeters behind, the CG of this battery is 15 centimeters behind the root chord, leading edge of the root chord, right? And also the CG of this wing, which is at the, coincides with the CG of the boom, okay? And let us assume that the CG, the weight distribution is, or say the CG of the wing is at the mid chord itself, okay? So this is another assumption we will consider. So what you can say is, the wing CG is at the mid chord. So about the taper axis itself, the CG of the wing is also present, longitudinal CG location. So now, from the given data, we will be able to draw the UAV schematic of this UAV. Let us say this is the boom, right, which is about 1.5 meters. So say this is 1.5 meters. Let me reduce this size, otherwise I may not be able to draw it to the scale. Draw it to the scale. Okay. So say this is 1.5 meters. 1.5 meters. Okay. And then I have a wing of 3 meters, and the CG will be at C by 2, isn't it? With a root chord of, say, 0.3 meters and the tip chord of 0.2 meters. Okay. So first let us figure out the taper axis, and we were told the CG is at the midpoint of the chord, of the wing itself. So let us assume this is the midpoint of this particular tube, right, or the boom, because it's a cylindrical boom, and then we can assume homogeneous distribution here. So the CG can be at the L by 2, right? So that's a decent assumption. So the CG is at, say, 1.5 meters. So the CG is at 0.75 meters, right? So with respect to the starting of this boom, the CG of this boom is at 0.75 meters, and the taper axis of the wing will also be at 0.75 meters with respect to this boom, starting of the boom, isn't it? Why? Because the CG of the wing coincides with the CG of the boom, and it presents at the midpoint of the chord, which is the taper axis itself, right? So this will be, say, my taper axis, which is the midpoints of the chord. Say this is my root chord. Root chord is given as 0.3 meters, right? So say this is my root chord. Let us say the root chord is 0.15 meters ahead and 0.15 meters behind the taper axis, right? So which is total 0.3 meters. Right? So this is my root chord CR, and say the tip chord again is tapered about the same axis. So what I have is 0.2 is the total chord. So I have 0.1 meters above the taper axis and then 0.1 meters below the taper axis here. Okay. So 0.1 meters below the taper axis. So this will be my wing. So I will join the leading edge and the trailing edge of all the chords here. So this is my wing, right. So similarly here you can assume okay, this is my wing of this UAV and the span of the wing is given as, so 3 meters, right. Okay, makes sense. Now I have root chord here CR, this entire part is my root chord, so the entire part is CR which is 0.3 and CT which is 0.2 from the given data, and the CG of this lies at the midpoint of the root chord, right, isn't it? So and it coincides with the mid CG of this boom which is at 0.75 meters with respect to the starting of this boom, with respect to the mouth of the boom, you can say here. Now we need to attach a motor to this boom such that the CG of this entire configuration, and again, yeah, just to add this point as well, there is a battery, right. So this battery weighs about, so let us say whatever the weight must be distributed. So the CG of this battery is also coinciding with the CG of the entire system because it was given the CG of the battery is at 0.15 meters with respect to the leading edge of the root chord. So this is my leading edge of the root chord, 0.15 meters from the leading edge of the root chord falls on this taper axis, which is in fact the CG of wing, CG of the boom as well as CG of the battery. Let us assume this is the distribution of my battery along the span which weighs about 0.3 kg, right. So and the CG of this battery is also at this particular location, right. So now what I can do is X CG of battery, so superscript here B stands for battery, okay. So X CG of the battery is at 0.15 meters, okay, with respect to the leading edge of the root chord, and the mass of the battery is 0.3 kg. So that is what it is given, 0.3 kg, 0.15 meters. And then the wing, XCG of the wing is at 0.15 meters again with respect to leading edge of the root chord, and the mass of the wing is about 0.45 kg. And we have the boom, so XCG of the boom is equals to 0.15 meters with respect to leading edge of the root chord, isn't it? So with respect to, so let us say 0.15 meters. So if I write, if I don't write anything beneath this CG, right, as a subscript to CG, so that means it is, we are measuring with respect to the leading edge of the root chord, okay. So and the mass of the boom is, so let me add BT for battery, right, BT for battery and BO for boom, okay. So BO for boom here, BT for battery, okay. So the boom mass is about 150 grams, right, 0.15 kg. So the boom CG can also be like, we can also take the CG length, CG reference with respect to the starting point of this boom. So the CG with respect to, or say, so the CG in all these cases with respect to the starting of this boom with respect to this point. So X CG of battery with respect to boom, right? Let's say WRT with respect to boom, BO with respect to BO is equals to 0.75 meters. In all the case it is 0.75 meters, right? It's a 0.75 meters. So similarly xCg of wing with respect to BO, with respect to boom, right? With respect to boom is also 0.75 meters, and xCg of battery with respect to boom is also 0.75 meters. Okay. We will see why we require this. So for this particular configuration, the CG is more or less same, isn't it? M1 x1 plus M2 x2 plus M3 x3 upon M1 plus M2 plus M3 sigma m, isn't it? So in all the cases, xCg is same with respect to the boom, with respect to the starting of boom. We can say the CG of this entire system, which includes battery, wing, and the boom, is at 0.75 meters from the starting of the boom, right? So let us say this is for the rest, what we can call it as, so m of rest, mass of the rest, apart from the motor that we have to add, mass of the rest is equals to mass of battery, okay, so is equals to mass of battery plus mass of wing plus mass of BO, boom, okay, which is equals to 0.9 kg, okay. We can add it, 0.3 plus 0.45 is 0.75 plus 0.15 is 900 grams, okay. So that's a, and the CG of all this, CG of rest, I should say, xCg of rest is equals to 0.75 meters. So with all these components together, the CG is also at 0.75 meters, okay. Now what do we need to find? So what should be the weight of the, so first of all, whether to talk about, if you have to talk about CM alpha, we need to know what is the aerodynamic center. So CM alpha we can talk only when we know what is xCg and xAC. CL alpha is positive. Let us, we don't go into those details of CL alpha right now, right? But if you want CM alpha positive or negative, that is governed by this distance between xCg and xAC. So I need to know what is the location of xCg and xAC of this particular configuration, right? First of all, let us figure out what is the current xCg of this location, right? And we know it is 0.75 meters, right? We want to know what is the aerodynamic center for this. So that means, so with the given data, we should be able to find out mean aerodynamic chord and project the mean aerodynamic chord onto the root chord and figure out the corresponding aerodynamic center with respect to leading edge of the root chord or with respect to the boom here, correct? So if you are talking about this particular equation, then let's talk in terms of leading edge of the root chord itself, okay? So CM alpha is equals to CL alpha of wing times x bar CG minus x bar AC of wing, right? So if this has to, so we know what is xCg here. So CL alpha of wing is equals to, with respect to leading edge of the root chord, it is about 0.15 meters. Am I correct? So this is 0.15 meters minus x bar AC of wing, right? So I need to find out what is x bar AC of wing. So how can I find? So first let me, I'll find out what is C bar. C bar is 2/3 CR times 1 plus lambda square upon 1 plus lambda. It's a straight tapered wing, right? So 2/3 times CR is 0.3 meters times what is lambda here? So lambda is equals to CT upon CR. So CT is 0.2 upon CR is 0.3, which is 0.67. Okay. So multiplied by 1 plus 0.67 plus 0.67 square upon 1.67. So it turns out to be, so C bar is equals to 0.254 meters. Okay. So C bar is 0.254 meters. So now project this onto the root chord. How can we do that?
See, we know this point, that is C bar by 2 and CR by 2, they lie on the same axis because it is the taper axis. So we know these 2 points lie on the same axis. You can simply, so if we want to know the difference between the leading edge of the mean aerodynamic chord and the leading edge of the root chord, it's simply CR by 2 minus C bar by 2, because this is the midpoint of each and every chord. If you project it onto the root chord, that's a midpoint here. Okay. So this is 0.254 is the total C bar. Let us say this is my total C bar, which is 0.254. If I project it onto the root chord, so what I have is, so let's say this is my mean aerodynamic chord, right? I projected it onto the root chord. So what I have is, so 0.254 is the total. Half of that will be 0.127, right? 12.7 centimeters. So above the taper axis it is 12.7, below the taper axis it is 12.7 centimeters, right? Which is 0.127 meters. Okay. So this is my C bar by 2. So this is like C bar by 2. This is also C bar by 2. Okay. So I know the aerodynamic center here, XAC, let us say, is at certain point. So with respect to leading edge of the root chord, it is at a distance of, so say this is my aerodynamic center, XAC. This is my, this point, yellow point is my AC. So AC we know C bar by 4. Am I correct? This is C bar by 4. XAC is C bar by 4 with respect to the leading edge of the C bar. Now, in order to find this location of aerodynamic center with respect to the leading edge of the root chord, what I need to do, I have CR by 2, I know C bar by 2 because this is tapered about mid axis, and subtract C bar by 2 from CR by 2. So what I have reached with respect to leading edge of the root chord is leading edge of the mean aerodynamic chord. So from there, 1/4 from there is my aerodynamic center. So what I mean here is X bar or XAC, aerodynamic center. So this is with respect to leading edge of CR, okay, is equals to, so there is no, see, this is by default we are doing this, we always consider it with respect to leading edge, but here there is a need for us to talk with respect to the leading edge of the boom as well. So that's the reason why, in order to avoid confusion, here we are talking about X aerodynamic center with respect to the leading edge of the root chord, right. So I have CR by 2, right, CR by 2, so CR by 2 minus C bar by 2. So with this I have now reached from leading edge of the root chord, I have reached to the leading edge of the mean aerodynamic chord plus C bar by 4. Okay. So from leading edge of the root chord, so this takes me from the leading edge of the root chord to leading edge of the mean aerodynamic chord. From leading edge of the mean aerodynamic chord, I am reaching aerodynamic center here, C bar by 4, right. So this equals to CR by 2 minus C bar by 4. Okay. So what is CR by 2 is 15 centimeters, right, minus C bar by 4 is like, so C bar is 28, right, so 25 centimeters upon 4 is approximately 0.0635. 6 4 is 24, right, approximately 6 centimeters, isn't it? So if you subtract this, what I have is 0.0865 meters. So with respect to leading edge of the root chord, this particular value, the location is at 0.0865 meters, which is 8.6 centimeters approximately. So if you move down to 8.6 with respect to leading edge of the root chord, you will find your aerodynamic center here, right. So now, so we got to know 0.15 is the CG with respect to leading edge of the root chord, and now you know the aerodynamic center of the wing, aerodynamic center of the wing with respect to the leading edge of the root chord. So can I substitute that value here? So what I have is CL alpha of wing times 0.15 minus 0.0865. This is equals to 0.6 or 0.635. So this value turns out to be that. So which is close to 6 centimeters. That means this is positive. So CM alpha is becoming positive here. So with the current CG location, it is positive without adding any motor. Now what we are asked is, what should be the minimum weight of the brushless motor that need to be attached to the straight at the starting of the boom, right? So we need to add some mass here. Let us assume that as this particular block. Now that motor has this particular block here. So say this is my brushless motor. I am attaching to the boom here. Okay, this is my brushless motor. So it is attached exactly. Let us assume the CG of this motor coincides with the starting point of the boom. Okay, that's one assumption that we'll consider. And now with this attachment, so the CG now has to shift forward. We know that, right? So what should be that minimum weight of this motor that makes this configuration CM alpha negative? Okay, is it clear? That means a mass of the motor, which is say mass of the motor mm, is the mass of the motor that I need to attach to make this configuration stable, right? So at least in case of CM alpha, that has to be less than 0. So now I need to talk everything with respect to the leading edge of the boom, because this is attached at the boom, right? So now I will try to talk about the CG location with respect to the leading edge of the boom. Okay. So for that, what I need to do, so what should be the minimum location in the first place, or what is the boundary condition when CM alpha is 0? Am I correct? So right now it is positive. If it has to go to negative, and there should be a point where CM alpha is also 0. There should be a CG location where CM alpha is 0. So what should be that location? CM alpha can be 0 when CG is equals to aerodynamic center. So now let us find out if so what is that weight that we are adding ahead of this wing that brings the CG to the aerodynamic center. See, right now the CG is at this taper axis, aerodynamic center is here, right? So I need to bring this CG of this entire configuration without motor, right, to this aerodynamic center by adding a particular motor. Now I need to choose what should be the minimum weight of that motor, right? So first of all, the minimum weight to make it CM alpha negative, we need to know the weight of the motor that we are going to add, right, that makes this aerodynamic CG coincides with aerodynamic center. Am I correct? Right? So first, if we find out that any mass more than that, we'll try to shift the CG ahead of the aerodynamic center that makes that particular CM alpha negative for this configuration. Okay? So I need to add, first of all, I will find out the boundary condition that makes CG coincide with the aerodynamic center with the motor, right? So CM alpha for me to become 0, right, which implies XCG should be XAC for this of wing. Am I correct? So just by substituting the CM alpha 0 in the previous equation, so what we have is this XCG must be equals to XAC of the wing, right? Now, if this has to be the final XCG, what should be the mass of the motor? Now, what is the total mass of the aircraft? Let us assume M represents the total mass of the aircraft, right? That is equals to, earlier it was like mass of wing, M of wing plus mass of battery, BT, and we have mass of the boom as well, right? So M of boom, BO. And now, so we call this particular expression like this as M of rest, right? So that is the reason why we used rest. And now what we have is, in addition to it, we are adding a motor, mass of motor, okay, which we need to find out in fact, right? So what I have here as an expression, M is equals to total mass of the aircraft is mass of rest plus mass of motor. So I know mass of rest is 0.9 kg, right? So mass of rest is about 0.9 kg plus mass of motor. Okay. And now with the addition of this mass at x, so what is the location of this mass? What is the CG location of this mass with respect to boom? So x mm is a mass of motor, and the corresponding x CG of motor is 0. It is exactly with respect to the boom, right? I am talking with respect to the boom, right? It is exactly at the leading edge of the boom, or you can say at the starting of the boom. Okay. So with that assumption, so the new CG I need is x aerodynamic center here, right? So the new CG, what I need is nothing but the aerodynamic center of the wing is at the aerodynamic center of the wing, which is about 0.75 meters. No, I'm sorry. So what is the aerodynamic center of this wing with respect to the boom, leading edge of the boom? Right. So I know what is this. So I know CR by 2, I know boom length up to here is 0.75 meters. I can subtract CR from here, CR by 2, plus what is the corresponding XAC. Am I correct or not? Am I correct or not? So now we are talking with respect to the boom. So XCG is equals to, so 0.75 is half of the length of the boom minus CR by 2 plus XAC of wing with respect to leading edge of CR. Okay, so this particular value is with respect to leading edge of the CR here, root chord. So 0.75 is length by 2, that is where the CG is, current CG is. Am I correct? Minus CR by 2 is the root chord. I'm subtracting this root chord from this entire length so that I reach this particular leading edge of the root chord. From there, again I am adding XAC, which is aerodynamic center with respect to the leading edge of the root chord. So this is equals to 0.75 minus 0.15 minus plus 0.0865. So this equals to, so the new CG with respect to the boom. So CG with respect to the boom has to be with respect to the boom, new CG. This is the new CG, okay? So new has to be at 0.065, which is nothing but the aerodynamic center, location of the aerodynamic center of the wing with respect to the leading edge of the boom, or say starting point of the boom, 0.6865 meters. So it is about 68 centimeters from the starting of the boom, right? So XCG, this is the new XCG. Now, in order to achieve this new XCG, what should be the mass that I need to add, right? Okay, so how can I find it out? So I am again erasing this part. So XCG, or the new XCG, or it has to be the X aerodynamic center, both with respect to leading edge or with respect to boom, starting of boom, is equals to M1 or mm motor mass times is the additional weight, right? So with this additional weight, we are trying to shift to the new CG from the current CG, which is nothing but the aerodynamic center of the wing. So mm times x CG of motor plus the rest, no? M rest times x CG of the rest upon total weight here, isn't it? Mm plus rest, M rest. Mm plus M rest is 0.9 kg. Okay. So I need to find out what is mm from here. Fine. So the new CG which I want is 0.6865. 0.6865 meters is equals to, so mm times 0, right, isn't it? Mm times 0, xCG of motor is 0, that's what we have, and plus 0.9 times 0.75
is the CG of the rest. You can see that. No, CG of the rest is 0.75 upon what you have is mm plus 0.9, right? Mm plus 0.9. So if you solve this, mm is equals to 0.9832 minus 0.9, right? So this mass of the battery is equals to 0.0832 grams, or sorry, kg, which is approximately 83.2 grams. So you need to at least choose a motor, right, which weighs about 83 grams in order to make Cm alpha 0. And now you need to choose anything more than this 83.2 grams to make it negative, right, Cm alpha negative. So in order to make Cm alpha less than 0, so I need a motor of mass which is greater than 83.2 grams. Okay, is it clear? So now if you find this 83.2, if you take any weight more than this 83.2 grams and you find the new CG location, then if you substitute that CG location and the corresponding aerodynamic center location in the equation, you will be able to find Cm alpha is negative, right? That is how you are shifting the CG ahead of the aerodynamic center here. So this is the motor that we require. Okay, we can solve the second problem now. So the second question question B for this is, assume the cross section of the wing in question 1 or question A is, so NACA 23112 airfoil, which is a reflex airfoil here, right? Reflex airfoil with the following data. What it is? Or say alpha and CL. Alpha is in degree. Okay. So first is at 0 degrees angle of attack. This is approximately 0.08, right? This is 0.08, and then at 6 degrees angle of attack it is 0.481. 6 degrees angle of attack it is 0.481. Okay, so this is the data given for the airfoil, right? And also the CMAC, so also the CM about aerodynamic center, or CMC by 4, so more or less same, no, unless there is a huge deviation. So CMC by 4 is close to 0.03, right, 0.03. So that's a reflex airfoil that we can talk about. We can immediately get to know that no, CMAC is positive, it's a reflex airfoil, and the wing CMAC and consider the wing CMAC is 0.9% of, or 90%, sorry, 90% of CMAC of airfoil, okay, or 90% of airfoil CMAC. Okay. So what do we require to find? First thing is, what should be the maximum weight? What is the maximum weight weight of the motor for which Cm naught is still greater than 0. Okay, so let's first look at the given data. So what do we need to do in the first place? We are asked Cm naught has to be greater than 0. Cm naught of this is equals to Cmac of the wing plus Cl naught times x bar Cg minus x bar Ac of the wing. Am I correct? Okay. So for Cm naught has to be positive, right? So this has to be, this is given as 0.03 times 90%, it is 0.9%, right? Multiplied by 0.9, which is 0.027 kind. Right? What is the value? 0.027, right? Okay. Plus Cl naught times x bar Cg minus x bar Ac of V. Okay. So this is 0.027 plus Cl naught times x bar Cg upon x bar Ac of V. So without adding the motor, we know what is the XCG, right? Isn't it? So it is at 0.75 meters and the aerodynamic center is behind, ahead of the CG, and we know this is positive, right? And this is positive, Cm naught is positive. By adding the motor, we brought CG ahead of the aerodynamic center, right? Isn't it? If we add a motor which is anything greater than say 84 grams, that means this quantity will be lesser than this quantity. Okay. This makes it negative, and so now you are subtracting it from this positive CMAC. The reflex aerofoil which you have considered to trim at positive angle of attack, now you are trying to compromise at that, right? By bringing the CG more forward. Okay. Now, say if we consider a motor which is heavy enough to make this particular quantity more negative than this CMAC of the wing. If you do so, then Cm naught becomes negative, right, which is undesirable in our case. Am I correct? That means first we have to find out that limiting condition. What we are asked, so what should be the weight of the motor that shifts the CG so much that it makes Cm naught negative, or say, or what is the maximum weight that you can afford? If we have to afford, then Cm naught has to be positive, right? Isn't it? So in order to trim at positive angle of attack, Cm naught has to be positive. So that means this particular quantity, the maximum weight, say the minimum weight is about 84 grams. Now say if you consider it 200, whether it should be 200 grams or 300 grams, that makes this still positive. So in order to get that answer, first we need to find out what is the limiting condition. When can Cm naught has to be 0? When can Cm naught become 0? What should be the weight of the battery I need to add such that this quantity becomes negative, right, or exactly equal to this particular quantity. Am I correct or not? So what will be the corresponding CG location for that? Aerodynamic center is not going to change, right? So only CG will change with the addition of motor. Now we know aerodynamic center of the wing with respect to boom there, isn't it? So now we can write with respect to the boom there. Okay, the distances we shift the reference to the boom right now, and then substitute them here and see and equate the Cm naught to 0 and find out what is the corresponding CG location. Once you know the CG location, you know that should be the CG that you need to achieve by adding a motor of mass m. So figure out what should be the maximum motor weight of the motor. Okay, got it? So if I have to shift this, let us say we'll find out the CG location with respect to the root chord itself. Then we'll try to shift it, right? First of all, this is with respect to the root chord of the leading edge. This equation is with respect to the root chord of the leading edge, right? So now x bar Cg or xCg should be equal to should be equal to minus 0.027 upon CL naught, right? CL naught of the wing
plus x bar or x AC of the wing, let us for the time x bar AC of the wing. Okay, this equals to x CG is equals to minus 0.027 upon CL naught times C bar plus x AC of the wing. So this entire thing is with respect to leading edge of CR. Okay, we know what is C bar. C bar is 0.285 approximately. Right? So first of all, we need to find out what is CL naught. In order to solve this question, we need to find what is CL naught. So from the given data, so I am plotting the given data here. So the information that I am having is at 0 angle of attack, say this is my alpha and this is my CL, 2D CL. Okay. So airfoil CL. So this at 0 angle of attack, I have CL naught of the airfoil, right? This becomes CL naught of the airfoil. So this is airfoil data, 0.08. So this point corresponds to 0.08 here. Okay. And there is another point. So this corresponds to 0. So there is another point at 6 degrees angle of attack. So what I have is CL as how much? 0.481. So this particular point corresponds to 0.481. So this coordinate corresponds to 6 degrees comma 0.481, and this coordinate corresponds to 0 comma 0.08. So say this is a linear regime. Okay, this is the linear regime that I am considering. So first of all, I can find out what is the slope of this curve. So this point corresponds to alpha at which CL is equals to 0. Right? So first of all, I need to find out what is the slope. So the two-dimensional slope CL alpha is equals to 0.481 upon minus 0.08, right, upon 6 degrees multiplied by pi by 180. So what is the value? So CL alpha is equals to 2D is equals to 4.6 per radian, right? This is per radian. So that's the reason why we multiply per radian. Okay. Now I have 2D CL alpha. I will be able to find out 3D CL alpha. Am I correct or not? So how can I do that? So 3D CL alpha is equals to CL alpha 2D upon 1 plus CL alpha 2D over pi E AR. So Oswald's efficiency was given earlier. So what is the aspect ratio here? You need to know what is the aspect ratio. So from the given geometry, it is aspect ratio is equals to B square by S, which is 3 square, which is 9 upon, what is S? What is the area of this?
Sir, CL alpha not getting 4.6.
Yeah, please make a correction, small correction here. This is not 0.4, this is 0.56. So consider this as 0.5614. Yeah. So if I have at 6 degrees, it is 0.56. It is 0.56. Okay. 0.56 this one. So if you substitute that 0.56, so what you have is 4.6 per radian here, right? Once you substitute this 4.6, so we need to find out what is the aspect ratio. So B square by S. S you can find out B by 2 upon CR plus CT, right? What is the value here? B by 2 is 3 meters upon 2 is 1.5 times CR plus CT is 0.75, isn't it? S is 0.75 meter square. Abhijit? 0.75 meter square. So this is aspect ratio is 12. Okay. So 900 upon 75 is 12 there. So 1 plus CL alpha is 4.6 upon 3.14 times 0.95 is the aspect ratio that we considered earlier. Sorry, 0.95 is the Ostwald's efficiency factor, and from the given data you refer to the previous question, and the aspect ratio here is 12. So the value is approximately 4.05 per radian. Okay. So CL alpha 3D for this particular configuration is 4.05 per radian. Okay. Now once you have CL alpha 3D, you need to find out CL naught 3D, right? So that may be, for example, so say this is my, so that is for infinite wing, this is for finite wing, right? So this is for AR infinity, so this is for AR 12, that is for AR infinity, right? So I know what is this lift curve slope 3D right now. So in order to find out CL naught here, this is the CL naught that is required, CL naught. So this is from here, right? CL naught point. But I don't know how to find out because I have only CL alpha 3D, right, for this blue curve. So but we know that it's a decent assumption to have to consider that the lift coefficient or the angle of attack at which the lift coefficient is 0 is same for finite wing as well as infinite wing. That's a decent assumption that we considered earlier. So if we can find out this alpha at which CL is 0, then I will be able to find out CL naught there, because I will have one point, another query point, and the slope there, right? So how can I find out that? From the airfoil data. So I know what is CL alpha 4.6, and I know CL naught from the given data. CL naught from the given data is 0.56, 0.08. So this is 0.8 from the given data. I have the slope as well. So I will be able to find out that. So alpha at which CL is equals to 0 is equals to CL alpha 2D minus CL at alpha 0 or CL naught, right? What is the value? Minus 0.99 degrees, which is approximately minus 1 degree. Okay. So this value corresponds to minus 1 degree. So this particular value corresponds to minus 1 degree here, right? So once I know what is alpha at which CL is 0, which is minus 1 degree, I will be able to find out this is minus 1 degree comma 0, this particular coordinates. So I will be able to find out what is CL naught. So how can I do that? CL naught is equals to CL alpha minus CL alpha times alpha at which CL is 0. Alpha at which CL is 0. This is equals to minus 4.05 times minus 1 multiplied by pi by 180, because CL alpha is in per radian. So what I have is approximately 0.07. So I have CL naught right now, and I know C bar, and I know with respect to the leading edge of the wing, I get to know, I can find out what is the corresponding CG location with respect to the leading edge of the wing. Right? So if I substitute that CL naught in this particular equation, so now the XCG is equals to minus 0.027 times 0.254 upon CL naught is 0.07 plus XAC of the wing is 0.0865. Okay. So if you do that, the new XCG, the new CG with respect to leading edge of CR, okay, so the same thing, is equals to minus 0.0115 meters. So approximately it should be 1.1 or 11 mm ahead of the, so this new CG, so has to be 0.011 5 meters, which is approximately 11 mm ahead of the leading edge. So this is the new CG. So initially the CG is here. Now adding a motor to make Cm naught 0. So a mass of motor that makes Cm naught 0. So further I need, cut this part. So this is the new CG location, which is 0.015 meters ahead of the leading edge of the root cord, right? So I need to bring the CG, which is from 0.75 meters to this particular location, the new CG location. So by adding a mass of motor, by adding a motor of mass mm, right? Okay. So I have this xCG here. So this must be the new location. Now the minus here indicates that the CG is ahead of the leading edge here, right? So now with respect to the boom, this location will be like length of the boom by 2 minus CR by 2 minus this particular length, right? So that is when I know what is this length. If I subtract this length, I am here, and if I subtract this distance further from the leading edge, which is the new CG location, I will be at the CG location with respect to the starting of this boom, right? So x boom, x CG with respect to boom is equals to L by 2, which is length of boom by 2 minus CR by 2 plus xCG. If you do a vectorial sum, it is this. Otherwise, you take the absolute value of it. Otherwise, plus xCG with respect to leading edge of CR. So this is how much? 0.75 minus 0.15, right? Plus, or this is minus 0.0115. What is the value? 0.5885. Okay. So the maximum weight of the motor has to be. So say if this is the CG, then so this is xCG with respect to the boom is equals to 0.5885. 0.5885, this one is. So this has to be this particular value. You substitute this value there and you will be able to find out the mass of the motor, the maximum mass of the motor that still allows Cm naught to be 0 or non-negative is equals to, so 0.2467 kg. So which is approximately 247 grams. Right? So you can add 247 grams here. If you add 247 grams, this makes Cm naught 0, right? That is how we calculated. So anything less than maybe 247 can be the maximum weight, right? That makes Cm naught 0, or 246.9 grams maybe, no? Or anything a gram less than this will make Cm naught positive, some positive value. Okay. So this is the maximum minimum weight, and how the CG shifts, and how you can play with Cm naught and Cm alpha of the configuration, right? So we'll continue with this with one more small example problem. What we'll try to do is, so assuming a motor mass of some grams, we'll find out what is Cm alpha and Cm naught of the configuration, right? So that will be the final exercise for today. So this is question 3, no? So or C. So assume the motor mass is 0.3 kg, sorry 0.2 kg. Find the Cm naught and Cm alpha of the UAV. Right? So simple question. So for the same data, you are given the mass of the motor as 0.2 kg. Here the mass of the motor is 0.2 kg. So the xCG, so solution, so we know Cm naught has to be Cm AC of the wing plus CL naught of the wing times x bar CG minus x bar AC of the wing. So this is with respect to leading edge of the root cords, and similarly Cm alpha is minus, so CL alpha times of the wing times x bar CG minus x bar AC of Okay. So now, first of all, we need to find XCG with this motor configuration. We know what is XAC of the wing. We need to find out what is XCG with this current motor configuration. So without motor, the XCG is about, with the rest of the mass, the XCG is about 0.75 meters. Okay. So the new CG with respect to boom is equals to mass of the motor times x CG of motor plus mass of rest times x CG of rest upon mass of motor plus mass of rest. Okay, so this equals to mass of motor is 0.2 times 0 because we are mounting exactly at the starting of this, and assume that the CG of this motor coincides with the leading or the starting point of the boom. Okay, so is equals to, so plus a mass of the rest is 0.9 kg times 0.75 upon 0.2 plus 0.9. So what will be the CG location with respect to the boom? 0.675 upon 1.1, it is 61 centimeters behind. Right? XCG is 0.675 upon 1.1, which is 0.6135. 6136 meters. So which is approximately 61.4 centimeters behind the boom, right? The current CG location is behind the starting of the boom, right? And located at a distance of 0.6 meters, 61 meters from the from the point. So now you need to find out what is Cm naught and Cm alpha. It's straightforward. So the Cm naught of the configuration at this CG location. So now I have to shift this CG location to, so this equation is either I need to take this distance with respect to aerodynamic center with respect to the boom, right, or with respect to the leading edge. So now I prefer shifting the CG from boom with respect to boom to with respect to leading edge of the root cord. Okay, so this is with respect to boom. Now if I have to shift this to XCG, so with respect to leading edge of CR, so what I need to do, so I know CR by 2, right, which is this distance. I know this reference point because with respect to this I know the leading edge. Okay, now I need to find out with respect to leading edge, I have to consider any one of the references. So I would like to prefer to consider this midpoint as the reference here. So with respect to this I know this distance, and from this point, otherwise vice versa, like from this point I know this distance, and from this point I know the CG location, right? So if I subtract that, those two from this, and what I end up is this particular the distance between the CG and the midpoint of here. Am I correct? CG and midpoint, let us say the CG is somewhere here, this particular point. Okay, so on this axis I just projected this at this particular point. So what I am trying to do is I am subtracting this distance from this entire distance, right? What I am end up with is this particular distance. Okay, now I have CR by 2. If I subtract this, I have that particular location with respect to the leading edge of the root cord. Okay, got it? So what I have is, first I am trying to subtract these two, the CG location with respect to the boom, which is 0.6136, right? So this will help me to figure out what is this distance, right? So now from CR by 2, which is like with respect to, from the midpoint, I am subtracting this difference, right? That will help me to find out what is the location of this point with respect to the leading edge of the root cord here. So this minus CR by 2. So from this I am subtracting that. So what I end up with is about 0.0136 meters. So 1.3 centimeters, like 13 mm behind the leading edge of the root cord. And my aerodynamic center is at
with respect to that, it is about
0.0865 meters.
which is 8.6 mm, right? This is like 8.6 centimeters.
this is 1.3 centimeters ahead.
Behind the leading edge, and that one is 8.6 centimeters behind the leading edge. So the aerodynamic center is behind the CG here, correct? So in that case, we have Cm alpha negative,
And see, we'll see whether Cm naught is positive or not.
okay? So with a motor of 200 grams, what will be the corresponding Cm naught and Cm alpha of this config?
That's what we are calculating right now. So Cm alpha is
CL alpha of wing times x bar Cg, which is 0 with respect to leading edge of the root cord, minus x bar AC, right? 0.0856 meters.
865, sorry.
865 meters.
So this is approximately
4.05 multiplied by
minus 0.0729.
so this equals to minus of 0.2
295.
yeah
closely minus 0.3, right? Cm alpha is minus 0.3,
and then Cm naught for this with this motor is
Cm AC,
which is 0.027 plus CL naught of the configuration is 0.07 multiplied by this particular difference, which is minus 0.0729, right? This equals to 0.021.
so okay. So Cm naught is positive in this case and Cm alpha is
Negative.
that satisfies the static stability conditions. Yeah, thank you.